recording this for YouTube. Hopefully this comes in handy for anyone on the internet and internally. I think what I'll do is start with this video. It just talks about tapers and kind of their importance. And then I'll explain tapers, what they are, why they're important, why there's variations in them, all those things.
Hello, I'm Jim, and this is the Mevotech Overbuilt video series. You know, it doesn't matter what size shop we're talking about. Time is money. And sure, it's important to keep that in mind. But unfortunately, sometimes that leads us to overlook things that ought to get more attention. Let's talk about suspensions, for example. When these are being serviced, some parts, like the ball joints, get a lot of attention, while other parts, like the steering knuckle, sometimes get overlooked. And our tech expert, Gordon, tells me that's unfortunate. Why is that, Gordon?
Well, it is unfortunate, Jim, because the steering knuckle is a key element of the steering and suspension system. The ball joints connect to the steering knuckle as well as the tie rods.
Okay.
And these steering knuckles have tapered receiver holes that are designed to accept the ball joint and the tie rod.
Okay.
And unfortunately, over time, and also through multiple ball joint replacements, the taper on these steering knuckle receiver holes can start to wear out.
Oh.
And when they start to wear out, that impacts the fit between the ball joint and the steering knuckle.
Wait, that's moving back and forth now.
That's right. So this fit should actually be very tight between these two. There should be no movement.
And when there is movement, what happens to the vehicle when it's up in operation?
Well, what happens to the vehicle is that there could be noise from this, and it's going to cause a lot more stress onto these ball joints from banging back and forth inside the steering knuckle.
Which means the ball joint doesn't last as long as it should.
That's right.
Okay, so how do we know when that taper is out of whack?
Well, when we're replacing them, if we'll take the ball joint, press it in there, get it into place, and then just give it a bit of movement back and forth, there should be absolutely no movement. It should be nice and tight in there. This part, unfortunately, has some movement and needs to be replaced.
So that's the key. When you're replacing the ball joint, make sure you test the fit before you certify the job is done.
Right, and before you test it, actually, I want you to make sure that they clean off this surface as well as these receiver holes. Make sure there's no rust or contaminants down in there. That can also affect the fit between the ball stud and the steering knuckle.
A little extra time, a lot of big results. There you have it. That's going to do it for this edition of the Mevotech Overbuilt video series. We'll see you next time.
Okay, so before we get into tapers and angles and all the fancy math things, let me explain why, Marshall, why tapered? Like, why not just use a bolt, right? And a lot of people will call that a bolt. A lot of people think because it has threads on the end of it, it's a bolt, or it's just, something holding the whole system together. So here's a pivot arm, and let's say we did use a bolt to bolt everything together, right? As you guys have learned, everything is connected, right? Pivot arm to the drag link to the steering arm, tie rod to the steering arm to the wheels, right? And as you've seen in other videos, wear is playing the system, right? There's something loose or moving. So if we used bolts, let's just say I bolted these two together, there's no way I could ever make this hole precision enough. I mean, I could, right? I mean, we could press the bolt in and there'd be no play in this system, right? Or between these two surfaces. So a bolt would require exact boring and press diameters and all that, which is a lot of, higher tolerances, more work, more during the manufacturing process, takes longer, adds cost, right? So, and the reason you can't have a bolt, another reason is, again, there's play. So Matt, when you tighten a bolt down, when you tighten the nut like that, you're relying on actually the bolt stretching, so it's acting like a spring, it's pulling, and it's trying to return back, okay? Or in very, very simple terms, the friction between this face of the nut and this face of the bolt head, right, is what's holding the two pieces together. So you're relying on that friction or that force squeezing down. So no matter what you do, this thing can still, with an impact or a bump or hitting, can slide in that hole, right? Like let me loosen it a little, right? It can move back and forth. So now multiply that times 6, 7 other joints in the system. And if they all start doing this, boom, 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 it compounds, it gets bigger, and now you got play in the system. And the part, right, the wearable part's still good. It's just that the mounting points are actually loose in the hole. So what does the taper do? The taper gets rid of all that play. So we'll get rid of this bolt. Again, another thing is you take this bolt, this nut falls off, let's say, okay? Vibrates off down the road, that falls out, right? Now you lose steering. Another disadvantage to a bolt. A taper, so I brought this big guy so everyone can see it. The taper we're talking about is this angle here on a stud. Ball joints have tapers, tie rod ends have tapers. Everything pretty much has a taper that's going to mount to a mating part. They're very, I'd say 99.9% are tapered. There's some older Chevy stuff that was a straight shank stud, but not likely. So again, this is the area we're talking about. You can see there's an angle to that. So in the mating part, there's going to be a taper in this part. So you'll see here, if I just put that in, you see how it's stuck? It does not fall out. It's where that bolt, the nut came off, it falls out. So these are called locking tapers. So all they are is a wedge. They're just a cone or a wedge. They have a wedging effect. When I put the nut on top here and tighten this down, so we'll tighten that and loosen it. In theory, and I wouldn't recommend this, but you can drive around without the nut on there. And I barely tighten this thing. So you can see now, even hitting that thing, how it's stuck in there, and I just barely tighten that thing. So, again, so why the taper? Mainly to take up any play in between the two mating parts. A bolt can flop around there because it's just a cylinder going inside a cylinder. A taper into a taper will eventually center itself and pull itself in, right? So let's talk tapers then. So these are the most common tapers. Jeremy has actually found, what were they, Jeremy? Like
2.4.
what brand vehicles though? Like Bentley or Volkswagen and Bentley, something like that. Or out, yeah. And there's even some newer stuff coming out now, but we'll just cover the 3 basic ones. So what you'll hear things referred to as ratios, or a 1-to-10 taper. There's a 1-to-8 taper, and there's a 1-to-6 taper. Those are just ratios. So we'll get into ratios here in a second. But all that equates to is the angle of that stud or that cone is 5.71 degrees. This is a metric taper, most common metric taper. Why? I couldn't tell you. I don't know the history of it, but most BMW, Mercedes, Volkswagen, some stuff, is this 1-to-10. Toyota, a lot of 1-to-10 stuff. So you can almost guarantee by the taper, I can tell you if it's going to fit a Chevy or a Toyota just by that. So probably just a standard. We're talking lean and all that. This is the standard the Europeans and Japanese markets have used. The most common one in probably every application in this building is almost all at 1-to-8. Or 7.125 degrees. So the angle of the cone is 7.125 degrees. Or another name you'll hear is 1.5 or 1.5 inches per foot. And all that means is for every 12 inches, you go up, it goes out 1.5 in diameter. Okay, so that's what creates that angle. So 1.5 inch by 12, or 1.5 inches per foot. For every foot it goes out 1.5 inches. And the other way is just 7.125. That's an easier way to talk about it. But this is very common. If you look online or anything, you'll hear about 1.5 inches per foot. A lot of people don't even refer to it as 1 to 8. We do internally, but if you look up reamers or anything online, they'll talk about 1.5 inches per foot. So the third next most common is going to be a 1 to 6 taper. It's 9.46 degrees angle, or 2 inch per foot. Same deal. And 12 inch of travel, it goes out 2 inches, like that. So it's the same, it's just a different ratio, but it's referred to as 2 inch per foot. Now, what are the difference between all these, and why are there so many? Why there's so many, I don't know. They should have standardized these things and made them all the same. I do know some history behind this one. If you'll look at my drawing here, it's as accurate as I can make it by hand. This is 5.7, it's a very narrow or flat angle. This one's 7.125, it starts to get greater. The 1 to 6 taper is 9.46, so it's an even greater angle. So the reason the 1 to 6 was made up was because aluminum started coming out. So aluminum steering knuckles, aluminum, knuckles of that nature, aluminum control, ball joints go into aluminum knuckles. So what happens is, so let's say, here's your steering arm, there's your taper in it. Okay, when you install a stud in here, remember it's a wedge, okay? It's going, you're pulling it in with a thread, okay? You're pulling that in. Aluminum is soft. It's not like steel or cast. So a 7.125 degree, pulling it into aluminum, since it's such a narrow angle, wants to just keep going. It will actually just pull itself clean through, and it can if you over tighten it. No one really follows torque specs, so they just tighten it until it feels right. The problem with aluminum is it may not ever feel right. You'll keep tightening and tightening, and like, it's kind of soft feeling, right? Well, you're pulling that, you're actually spreading this hole out, the part that it's going into. So they came up with a larger angle, 9.46, 9.5 degree roughly. So again, it's just a bigger angle. Exaggerate that, so that when you pull it up in, it's acting more as a shoulder or a larger angle. It's harder to pull through the aluminum. So when you see a 1 to 6 taper, almost guaranteed it's going to fit some type of aluminum. 1 to 8, it's going to fit steel, some type of steel knuckle application. 1 to 10, almost always metric. Now, the big thing to worry about, anyone that's going to samples or checking parts here, is these cannot be interchanged, and I'll explain that really quick why. So let's say you have this angle, let's say this taper here is the 9.46 degrees, okay, from here to here. And I install the wrong stud in this hole. So a 7.125. So it's going to be like this, right? Less. 7.125. Again, exaggerated. It's hard to see this by by your naked eye. This is exaggerated. You're going to have a gap. All this here is a gap. It's going to hit at the top and not at the bottom. So remember, there's a ball on the end of here, right? And it's connected to another part, and it's pushing at all times. When you turn the steering wheel, you're pushing, which is moving that motion. So if there's a gap in here, it's going to try to push that stud sideways, just like the bolt example. Remember the bolt example is, here's our hole, here's our bolt going through, head on it. You got a gap in here, right? So it's gonna clunk back and forth, same thing. Say there's a ball on the end here. If I'm pushing on this, it's trying to push it at an angle. The same thing happens here. If you put the wrong taper in the wrong hole, it will move. And they talked about the taper being bad, you know, in the knuckle in that video. The same thing can happen there. But more importantly, it's not that it just moves or can rock in this hole. So picture this. So we have a nut on top here, right? It's parallel with the surface it's mounting to. If I push that, this nut wants to stay square, but this thread wants to match the angle here, right, of the ball. So you do that 100, 200, 1,000 times. Eventually what happens is they fatigue and the threads pop clean off. And then the other problem is you don't have a good taper. Remember how I tightened that one and I could barely pop it out? Well, this never seated right to begin with, right? They're not a matching angle. So this falls, this pops off, breaks, the part falls clean out of the hole. So it's super important, like the video said, to inspect the mating part, but also more importantly is people need to understand that there's actually different tapers, because if I try to put that and that, and it works in reverse too. So if I tried to put that in that hole, it's just gonna hit down here at this bottom, and then there's gonna be a gap at the top, and that's gonna rock at the top. So I brought, so this is 1.5 inches per foot. This is a 2 inch per foot. So I'll pass this around and just drop both in each hole. You will see it's not very much, but it is enough. And I don't know if you guys can see that, but it rocks. So the 2 inch per foot does not mate well or match the mating hole. So I'll pass these around. And if anyone's curious, most people here know, because it is such a critical thing, we've made our own gauges. So we talk about standards. So we have our own gauges. This is a 2 inch per foot that we can check any stud up to that diameter in. And on all it is, these are just a bunch of tapered holes in a series of diameters that we can put it in. And we make one for the 1.5 inches per foot. And we also make one for the 1 to 10, the metric. You can almost see by the use of these things which one we use more. The 1 to 10 is like brand new look, so it's not a very common one. 1 to 10, you'll also notice not a lot of difference between degrees. These two can get intermingled pretty easily if the hole you're checking in is slightly damaged. Let me give one last example of a damaged hole. It's the same problem. So let's say this last example is putting the wrong stud in the wrong taper. So let's say, again, this taper has a dent in it, okay? Has something damaged on it. But when I go to mount this stud in here, it may fit like that, right? Ball here. But it's only going to be touching on one spot, or there's a dent out here, there's not much contact. So that in that knuckle example, if it's damaged inside or you don't clean the hole, like when you take this apart, if water gets down in here, which it shouldn't if it's a perfect match, it does not get in there. But water can, and it rusts and pits. So debris, dirt, rust, anything that gets stuck in here when you go to reinstall that part can prevent those two angles from matching well. And then it will, over time, move and rock. And the more it rocks, the more it makes this hole bigger until the bottom is all wallowed out like that. And then eventually the thread fatigues and pops off. It's guaranteed to happen. It's not can, it will happen. There's just no way around it. So if you ever do, one of the classic signs of, from a warranty perspective again, is if you see something broken right here, it's almost guaranteed they either had the wrong taper in the wrong hole or the taper they put it in was bad to begin with. The only way these become bad over time is if this nut came loose and this stud started turning in this. Once they're locked, they should never turn, okay? It should not turn inside that hole. It's not made to do that. It's made to go in and lock, and then the ball is where all the pivoting is done. So, anyways, taper, and there's a million more things to talk about tapers, but that's the basics as far as a safety factor. They always have to match, and they always have to be a good, clean hole without any damage or anything like that.